So we are just about done talking about implicit differentiation. We're going to do just a couple more examples of a little bit more complicated implicit differentiation problems, and one more example of using implicit differentiation to find the derivative of a function that doesn't look implicit. Okay, so let's start with this complicated one here. We want to find the derivative of sine of y squared plus 2y plus 1 plus cosine of 2x to the 6 minus 12 is equal to 3y plus 10x. This is kind of a mess, and this is clearly implicit, right? It's not an equation that looks like y equals something. All right, so this is going to require implicit differentiation. Now the right-hand side is easy enough to do. This is a pretty simple implicit differentiation problem, but the left-hand side is complicated because not only do we have to use implicit differentiation, but we need to use the chain rule as well, right? We have sine of not just x, but sine of y squared plus 2y plus 1. Okay, so when we take the derivative with respect to x on both sides, which is what we do when we're using implicit differentiation, we take d dx of both sides. Let's think about what's going to happen on the left-hand side. We have to find the derivative of the outer function with respect to the inner function. So the derivative of sine would be cosine, and we leave the inner function alone. So cosine of y squared plus 2y plus 1. But then we multiply that by the derivative of the inner function. Now remember, we're using implicit differentiation here. So anytime you take the derivative of a y term, you multiply by y prime. So the derivative of y squared would be 2y times y prime. Plus the derivative of 2y would be just regular 2, but we need to multiply it by y prime. And the derivative of the constant term 1 is just 0. Okay, so that's the derivative of my first term here. All right, now we take the derivative of the second term, cosine of 2x to the 6 minus 12. Okay, again, the derivative of the outer term with respect to the inner term would be the derivative of cosine is negative sine. We leave the inner term alone, 2x to the 6 minus 12. And then we multiply that by the derivative of the inside. Right, this is a little bit more simple. We don't have to worry about implicit differentiation here. The derivative of 2x to the 6 minus 12 is just 12x to the 5th minus nothing. Right, derivative of 12 is 0. Okay. Right, you could just write that as a negative sign if you wanted to. You don't have to do plus and negative. Okay, that's my left-hand side. Now I still have to take the derivative with respect to x on the right-hand side. The derivative of 3y would be 3 times y prime. Anytime you take the derivative of a y term, multiply by y prime. And then the derivative of 10x is just 10. Okay, this looks okay so far. Now remember what our next step would be. We need to gather up all of the y prime terms on one side of the equation, and everything else moves to the other side of the equation. That seems simple enough, except, well, we have sort of two y prime terms inside parentheses over here. All right, so let's maybe just leave them together for now, but leave this as well, right? Leave the cosine part because it's being multiplied and it's not really easy to get rid of that quite yet. All right, so this is what I'm going to do. I'm going to move 3y prime over to the right-hand side of the equation, and I'm going to move all this sine stuff over to the other side of the equation. Okay, let's rewrite this. We're going to end up with cosine of y squared plus 2y plus 1 times 2y times y prime plus 2 times y prime. I move the 3y prime to the left-hand side by subtracting on both sides. So we'll have a negative 3y prime. And everything else gets moved to the right-hand side of the equation. So we have a 10 already. And we move this negative sign over to the other side. The sign changes and it becomes positive sine of 2x to the 6 minus 12 times 12x to the 5th. All right. Now we factor out a y prime from each of these terms, and what do we get? Oof. Well, we can really factor out just a single y prime from here, because this cosine, think about it as sort of, right, it doesn't have any y primes in it, so we can think about it as just sort of a coefficient on the outside, and on the inside we have these y primes in each term. So we can factor out a y prime here, and it'll be times cosine of y squared plus 2y plus 1, then times 2y plus 2, right? We factored out these two y primes here. And then we also need to factor out a y prime of our second term, so we're left with just a -3 on the inside. On the right-hand side of the equation, we have 10 plus sine of 2x to the 6 minus 12 times 12x to the 5th. And finally, to get that y prime by itself, we divide by everything inside the parentheses, which is going to be cosine of y squared plus 2y plus 1 times 2y plus 2 minus 3. Right, all of that business cancels, and on the left-hand side, we're just left with that y prime we were looking for. And we get, okay, I don't actually feel like writing it again, it's this. Right, you could copy it out again if you wanted to, but this is the y prime that we're looking for. Okay, this mess of a function here. Okay, you can see when you use implicit differentiation and the chain rules required, it gets super, super messy, and you have to be really careful with your algebra. If there's any steps in here that you're not sure where it came from, just send me an email or write a comment so that I know and I can explain. Okay, one final example, something called logarithmic differentiation. So we can use what we know about logs and what we know about implicit differentiation to find the derivative of some really strange looking functions. So for example, if we wanted to find the derivative of the function y is equal to x to the sine of x. Now, do any of our rules really apply here? Not really. It's not like we can use the power rule, because it's not that we have x raised to some actual real number power, right? X is being raised to the sine of x. And it's not like we can really use the chain rule either, because we only can use a chain rule if this base was itself a real number. Okay, so it's not, none of the rules that we currently have would apply here. So, as a quick review, for anyone who's forgotten anything about logs, or perhaps everything about logs, one thing to know is if you're taking the log of x raised to some power c, c doesn't even have to be just a real number, it can be anything, it can be its own function. You can pull that c down in front as a coefficient. Right, so ln of x to the c power is equal to c times ln of x. This is a fact that we're going to use whenever we use logarithmic differentiation. Okay, so whenever you're dealing with a function which has x raised to some other function of x, in other words, you have x's in the base and in the exponent, then we use logarithmic differentiation, which involves taking ln of both sides. In other words, we're plugging each side of this equation into the natural log function. So we have ln of y is equal to ln of x to the sine of x function. Now the reason we're doing that is we want to make use of this fact here. This fact about logarithms allows us to take something that was an exponent and bring it out in front as a coefficient, right? And so what we have here is this exponent sine of x can be moved out in front as a coefficient. So now I can rewrite this as ln of y is equal to, pull that sine of x out in front, sine of x, times ln of, well, now that we've moved the sine of x, this is just ln of x, right? This sine of x got moved out in front, so we're just left with x inside the log function. And this is great. We know how to take the derivative of this. It's implicit differentiation on the left-hand side, and on the right-hand side, we just used a product rule. right? So as scratch work for my product rule, let's just do a little bit of scratch work here. My two functions here are sine of x and ln of x. Sine of x has the derivative of cosine of x, and ln of x has the derivative of 1 over x. Right, we learned that in the last video. So product rule is going to have us multiply across like that. All right, so we take the derivative with respect to x of both sides, and we get the derivative with respect to x of ln of y is going to be 1 over y times y prime. That's using implicit differentiation. The derivative of ln of y is 1 over y, and we have to multiply by y prime. And on the right-hand side, using the product rule, we have this derivative sine of x times 1 over x, sine of x times 1 over x, plus ln of x times cosine of x. Now remember, we're trying to solve for y prime here, so we need to get rid of this factor of 1 over y on the left-hand side. To get rid of a factor of 1 over y, we just multiply both sides by y. Not y prime, just regular y to get rid of that y in the denominator. Those will cancel, and we'll be left with y prime is equal to sine of x times 1 over x plus ln of x times cosine of x, all of this times y. Now this is a perfectly good derivative, it's just implicit, whereas our original function up here was explicit, right? It was written in terms of just y equals something, which means we can rewrite this implicit derivative explicitly using the original definition of y as being equal to x to the sine of x. In other words, plug this x to the sine of x in for y at the end. So we get that the derivative is going to be sine of x times 1 over x plus ln of x times cosine of x, all multiplied by, instead of a y on the outside, I'll just plug back in x raised to the sine of x power. And that's our derivative. Which is kind of neat. And the great thing is, all of these problems end up being pretty similar. They all end up having to use the product rule and having to use sort of this substitution at the end again. They have a similar feel to them. So we'll do one more together just as practice, and then you'll see that there's more in the exercises for further practice. So for example 2, we have the function y is equal to x raised to the square root of x. Notice we have x in the base and in the exponent, so this suggests to us that we're going to be using logarithmic differentiation. So just like before, to use logarithmic differentiation, we take ln of both sides. So we have ln of y is equal to ln of x to the square root of x. Okay, and the whole reason that we do this is we want to be able to take this exponent that's stuck inside the log function and move it out in front so we don't have an exponent anymore. So I can rewrite this as saying ln of y is equal to the square root of x times ln of x. To take the derivative of this, I use implicit differentiation on the left-hand side. And on the right-hand side, of course, I'm going to have to use the product rule, my two functions being square root of x, or x to the 1/2 power, and then ln of x. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2, and the derivative of ln of x is 1 over x. So this is what I'll use for my product rule. And by implicit differentiation, I get the derivative of ln of y is 1 over y times y prime. On the right-hand side, the derivative of square root of x ln of x is going to be x to the 1/2 times 1 over x plus 1/2 x to the negative 1/2 times ln of x. We want to get y prime by itself, so we multiply both sides of the equation by y. And we have y prime is equal to x to the 1/2 times 1 over x plus 1/2 x to the negative 1/2 ln of x times y. But just like before, it's nicer if we can write this explicitly if we don't have any y's in our derivative. So instead of writing a y here, I'm just going to substitute back in our original y function, which was x to the square root of x. And that's our derivative. Okay, you'll see some more of these in the practice worksheet.